Hello, everybody, and good evening. First, I'd like to thank Stacy and Florence for inviting me to speak to you all today. And then also a big thank you to all of you here for joining me and allowing me to be able to talk about my favorite planet, which is Venus. As Stacy mentioned, I am a planetary scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland. And I am also the deputy project scientist of DAVINCI, which is one of the next missions to Venus. And I am very excited about that mission, and I'm very excited about Venus, and I am really looking forward to sharing some of that with you today. So Venus that we know today, and what we're expecting to see when Da Vinci arrives there in about a decade, actually presents a puzzle. And what we know is a disconnected set of mosaic tiles, which are woefully incomplete. There has not been an atmospheric probe or a surface lander at Venus for over 40 years. And by the time we get there as, the Da Vinci mission, it'll actually be over 50 years since there was a visitor to the Venus atmosphere and surface. So what we currently know, primarily the most recent data that we've received is from orbiting spacecraft. And this has provided us with some astounding discoveries, but it has also left us with a plethora of remaining questions. So since I kind of, let me jump forward just a little bit and just while I'm going to talk about Da Vinci in detail later, let me just say, first of all, that we have kind of two components to the mission. First of all, we have the spacecraft, which will fly around Venus. It'll conduct 2 flybys, but also it has an atmospheric probe component. And so what I'd like to do with this talk right now is to help have us pretend for a minute that we are the atmospheric probe itself, and to see what would it be like if we were to sit on this probe or sit in it as it drops through the atmosphere, and what would we see? So to start with, as our spacecraft approaches Venus, the first thing that we notice is that she is an atmosphere-dominated world of approximately Earth size, and it has a curious rotation. So if you are able to see this screen, you should notice that what you're seeing here are just kind of some browns and yellows and white clouds, where you're not able to see any surface features. And then also, you'll notice that it's actually orbiting kind of backwards than what you would expect. It's the only planet in our solar system that rotates backwards. Additionally, Venus has no seasons, and so her axis is nearly vertical. And what this means is that since there's going to be no seasons at the surface, it's primarily all the same. It's going to be all the same temperatures, all the same pressures. And so her atmosphere is very thick, and as I said, it's very opaque, so we're not able to actually see any surface features. But if we pause for a moment, you'll see a cloud feature that was recently observed by Venus Express, which was an a European Space Agency mission, and was then further studied with the Akatsuki spacecraft. And Akatsuki was a mission from JAXA, which was the Japanese Space Agency. And this, let me throw up an additional slide here. There we go. This cloud feature, which is that kind of bright, almost vertical shape on sort of the left-hand side of the limb, it's kind of left center, continuously stays above the same area on Venus. And so that was rather curious to us. You know, there's this cloud feature that's almost in the exact same place all the time. And what we found is that this cloud is actually a gravity wave. And it's a wave caused by the upward forcing as air moves over Venus's mountains. And this becomes more obvious in this video that's showing the wave forming and staying above Venus's topography. Let me see if I can, there we go. So it'll kind of go back and forth a little bit, and you'll see this vertical structure that just kind of stays directly over one spot. And the kind of white section, little white lines underneath are actually some topography lines. So what's happening here is as this planet spins, air is actually getting pushed up over this higher topographical area. It's moving up in elevation and is basically pushing the rest of the atmosphere up always. And it goes kind of up and it goes kind of down, but it always stays in this same region. So let's move on. We've now seen above the clouds, so let's now drop down into the clouds. And this brings us to the mid-level cloud layer. So if we stop our descent in this mid-level cloud layer, we find ourselves in an environment that's not too different from Earth in terms of temperature and pressure. And because of these reasons, scientists hypothesize that Venus's clouds could actually host microbes in them, just like Earth. Additionally, Venus also has lightning, but unlike Earth, its clouds rain sulfuric acid, which creates quite a hazardous environment that we would not enjoy staying in for very long. But if we push through this infernal atmosphere, eventually we see the surface. And here we find an arid landscape with temperatures that are hot enough to melt lead. These temperatures are approximately 465 degrees Celsius at the surface. So that's in the high 700s Fahrenheit. Actually, sorry, high 900s Fahrenheit, so like around 960, I believe. And then also pressures that are 100 times that of Earth. Venus is also largely flat, but there are several mountains and highland areas called tessera that rise above the low-lying plains. And these tessera regions are, some of these are regions that we actually have not found on any other planet. And they are also expected to be the oldest landforms on Venus. A lot of Venus may have been restructured by prior volcanism. But the tessera regions, because they're high altitudes, we kind of expect that those have not been resurfaced. And this will come into play later on. So the surface, while constantly shrouded by clouds, has more secrets to reveal, but also raises some more questions. One mystery that eludes us is that there's evidence that there may be a metallic snow on the side of some mountains. So what I'm showing here is Magellan data of Obda Regio and color-coded with emissivity. Obda Regio is a higher elevation and therefore cooler temperature region, is at the left side of this image with the cooler colors. So those the blues and those purples that indicate a lower emissivity, which is basically like how much, how like sort of shiny a surface is, which allows us to get different data reading from it. And so these emissivity measurements actually can tell us what the surface is like, whether it's like really rocky, but also composition. And so these cooler areas, these lower emissivity values, while at high altitude regions, are showing us that the composition that it's measuring right there is going to be a different composition than the lower lying regions where these warmer colors are. And so we don't know actually what for sure is causing these lower emissivity values. There's a lot of data, or sorry, there's a lot of experiments that are being conducted on it. And some of the hypotheses are that there is a precipitate out of the clouds that falls onto these higher elevated regions where it's cooler, and they kind of sit there, similar to how we have snow on the sides of mountains. But instead of being, instead of that snow consisting of water like we have, it's going to be some sort of metal, because again, Venus is very, very hot and only metal can consist in some sort of liquid form. And so we won't actually know for sure whether this is metallic snow whether it's a snow or frost or actually just some sort of type of rock, until we actually go to Venus and we're able to test the surface. And so this is just kind of showing, it's just a nice little animated GIF of the same, kind of the same area, and showing there are different measurement values that we get in higher altitude regions compared to lower altitude regions. So also emissivity has shown us that Venus is likely volcanically active. This image here, sorry, this GIF that I showed, I'm just going to kind of pop it right back up again, is a volcano called Idu Mons, and it's overlaid with emissivity, which is derived from an instrument that flew on Venus Express. And the higher thermal emissivity values here, these warmer colors, correspond with the higher elevations. So this is kind of what we know Venus is like now. It's a dry, hot landscape that is likely volcanically active. But we don't know if Venus was always like this. Or did it once have an ocean of liquid water? Maybe it had oceans that also had continents that rose above the oceans. There are several studies currently that suggest that Venus may have had oceans for billions of years. And so it may have been once Earth-like before something happened that turned it into this really hot, high-pressure, raining sulfuric acid, potentially snowing metal world that we know now. But you know, these are two very different environments. And so what we want to know is what was the evolutionary path that Venus followed? Was it once like this screen here, where we have you know, these oceans and these continents, where water may have existed, or has it always been like this? And some of the missions that are going to be flying to Venus within the next decade are looking to solve this this puzzle. And so the mission I'd like to speak to you today about is DAVINCI. And DAVINCI is the Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. And I'm very happy that I included that on the slide, because I'm always forgetting the name and it's very embarrassing. But this is a mission that I've been working on with a fabulous team. I am the deputy project scientist, and I primarily work with the principal investigator, Dr. Jim Garvin. We have two deputy principal investigators, Dr. Stephanie Getty and Dr. Giada Arni. And I also work with the project scientist, Dr. Natasha Johnson, and we are very excited about this mission. We all are enthusiastic about Venus and very excited that we are going to be able to actually send a probe into the atmosphere to learn more about the planet next door. And so DAVINCI itself will make critical missing measurements, missing because remember I said earlier, there has not been an atmospheric probe in the atmosphere of Venus for over 40 years. And we're sending flight proven instruments in order to answer some fundamental unknowns. First of all, you know, did the inner planets form from similar materials? Or did Venus once have an ocean? Did it look more like Earth, or did it always was it always very hot and dry? What about volcanism? Has there always been volcanoes? Were there more volcanoes before and less now? And then also, what is the composition of the surface itself? Does that tell us whether or not there were previous continents? What's going on with the weathering on the surface? And how we investigate what Venus is of today informs us of what Venus is of the past. And we use tools, we use flight-proven instruments that we've flown to places like Titan, Jupiter, Mars, and then also instruments that we use here on Earth, so that we can learn more about the chemistry and the isotopes of the atmosphere, to put what we learn in context with Venus and with the rest of the solar system planets. And this will enable us to know if Venus could have once had this long-standing surface ocean like Earth or not. And so to answer these big unknowns about Venus and to complement objectives of other missions that are flying to Venus, we will actually plunge into, we will send an atmospheric probe to plunge an analytical and imaging payload into the atmosphere to comprehensively investigate the upper and lower composition of the atmosphere. So we're going to be taking measurements as we fall all the way through. And then we're also going to take images of the Tessera region, Alpha Regio. And Alpha Regio was actually one of the first planetary environments that was ever imaged of another planet. It was originally imaged by Arecibo telescope. And so I want to walk you through a little bit through our instruments. We have on the spacecraft itself, we have VISOR, which is a Venus imaging system from orbit for reconnaissance. And what that's going to do is it's going to be taking measurements. It's going to be seeing into the atmosphere so that we can learn more about the atmosphere itself, and then also of the surface. And we have a tech demonstration called a CUVIS, which is the Compact Ultraviolet to Visible Imaging Spectrometer, which is going to be taking images and movies of the atmosphere. And then on the probe itself, so what's going to be entering into the atmosphere is a mass spectrometer, VMS, which is paired with another type of mass spectrometer, VTLS, in a configuration that is actually very similar to the two mass spectrometers that are currently part of missions to Mars. And then we also carry an atmospheric structure package called VASI, which will study the structure and the physics of the atmosphere. So taking temperature measurements, wind measurements as we go through the atmosphere. And this will allow us to obtain unprecedented in situ three-dimensional views. That is with our Vinci camera, which is the Venus Descent Imager. And it will be taking images as we fall down once we get past the clouds, so that we can better understand the surface composition of Alpha Regio. And then additionally, we have a student collaboration instrument called VFOX, which is a small oxygen sensor, and that will tell us a lot of really important information about the amount of oxygen that exists at the surface. So these are our 7 instruments that we're flying, and they will all work in concert to help us answer a lot of these unknowns, these unanswered questions at Venus. And these will provide us with science measurements with outcomes at each step, and each with different vantage points, but they are all interconnected via measurements and outcomes. They will provide us gigabits of new data during each phase with measurements never before achieved at Venus. So these phases that I talk about, we will be conducting 2 flybys, one in, if I remember correctly, one in 2030 and the other in 2031. And these flybys will be taking measurements with our VISOR instrument and CUVIS, and they'll be looking at the atmosphere and taking some surface measurements. And those will be conducted to prepare us for the probe entry and descent, where we are sending the other 5 instruments that will be taking data as we fall through the atmosphere. And our fall will take around an hour. I think it's exactly 59 minutes that we are expecting it to fall through the atmosphere before coming into contact with the surface of Venus. And so I'll take just a quick moment to talk about the scientific products that this payload will provide to the Venus community. From our flyby science to our descent, DAVINCI will connect the atmospheric measurements to the surface topography and composition. And these will determine how, these will help us answer questions on how Venus formed early in the solar system and what has happened to it since then, providing a better understanding of its evolutionary path in context with the rest of the solar system. So we want to know whether Venus once had water on its surface, and if it did, was it once like Earth? And so to do this, we need to go back, and we are going back with DAVINCI to learn how Venus has evolved so differently from Earth and the other planets in our solar system. And also, an added bonus to this is that Venus will tell us a lot about our own solar system, but it's also going to help us learn about planets outside of our solar system as well. Because evidence suggests that Venus analogs, so Venus-like planets, may actually be common, and they may actually be more common than habitable Earth-like worlds. This plot that I'm showing here shows the Venus zone. And so that's a zone around stars of different temperatures where we might expect to find Venus-like worlds. And when we attempt to decode the data we obtain from exovenuses, so exoplanets that are like Venus, computer models will help us understand what we may be looking at. But those models are only as good as the data that's used to constrain and validate them. And for that, we have to turn to Venus herself to provide the ground truth that we need to extrapolate these models to exoplanets. And with the James Webb Space Telescope, we are expecting to find more of these exovenuses. So the image on the left was a composite image taken by the Venera 13 over 40 years ago. And this rendition is one of the only images that we actually have of the Venus surface. So until we return, today's art can imagine being at Venus in the next decades, and in the eyes of an artist, Venus and her atmosphere is a curtain of wonder to explore.